Okay, and finally there's me, almost finally, that's me. So I'm David Crandall. I work in computer vision, which you can think of these days as machine learning and artificial intelligence applied to imagery. And the world is full of imagery. Something like 1 trillion photos were taken last year. Something like 8 zettabytes, that's 8 trillion gigabytes of data, visual data were collected in 2017 alone. Way more data than anyone can really look through or organize on their own by hand. Fortunately, computer vision techniques are starting to get pretty good. In some cases, in very limited cases, overhyped cases, in my opinion, they're actually working better than humans. And so this nonetheless means that there's a real opportunity here for helping people organize and understand large-scale image collections that right now are just not being understood. And so I'm going to give you just a couple of examples of some of the work that we do in our lab, arranged around some applications where we can make a difference using computer vision. For example, we've done a lot of work with social images, helping people organize their own imagery. So given an image, you have this long-standing interest in telling you where on Earth this photo was taken based only on the content of the image itself. If GPS is not available, say. We're also looking at how we can organize large-scale collections of images. For example, this is a 3D reconstruction that we've created of the Croatian city of Dubrovnik, based on some tens of thousands of photos downloaded from Flickr. And not only can we tell you where everyone in this place was standing, those little cones on the bottom are, but we can actually reconstruct a 3D scene based only on the information in the image itself, which helps us organize and reconstruct things about the world. Here's another application, completely different, but still about reconstructing the real world from imagery. So with Jeffrey Fox and folks at University of Kansas, we've been working with polar scientists on reconstructing, building models of the polar ice sheets and how they're changing over time. Polar scientists can now collect terabytes of data from ground-penetrating radar systems, but the data they get out is very complicated, it's noisy, it involves a lot of human labor to actually make sense of it. So we're working on 3D reconstruction techniques applied here so that we can create actual 3D models of the ice and how it's changing and help people visualize it better. Here's another completely different example. You probably all know that our lives depend on microelectronics and semiconductors and integrated circuits. What you might not know is that a lot of these are counterfeit. In fact, if you want something new to worry about, you're welcome. 20% roughly of the ICs that the government buys turn out to be counterfeit. And so this is a big problem. And we're working with Crane and now the Applied Research Institute to help use computer vision techniques to maybe to help counteract this problem. So for instance, we can spot subtle visual differences in the external packages of integrated circuits that might indicate that they're counterfeit. More recently, we've been looking at actually the microscopy images of the surface of the silicon itself and trying to spot irregularities that might indicate some defect or some Trojan that's been inserted inside a device. Many other applications we're also interested in, from surveillance to pathology and medical imaging to satellite imagery. More recently, we've been working on wearable cameras data. So this is data from things like GoPro, where you get a lot of data about somebody's day, a lot of visual data. It's really hard to organize it using manual techniques. I think Linda Smith will be giving a talk in the next session. We'll talk about our interdisciplinary collaboration there, which is really interesting, and I'll save most of that for her. But the basic idea is that she and Cheng Yu in psychology put cameras on kids, cameras and eye gaze trackers on kids, and then watch them as they go throughout learning tasks, as they learn to navigate the visual world, as they learn the names for new objects. And then they're interested in how kids learn and what the right strategies for learning are. Now, a key part of this in her work is actually annotating these images sort of frame by frame, paying people to annotate frame by frame, what is the child looking at, what are the objects in the scene, and so on. Well, with computer vision now, we can help ease that and really speed up the rate that she can understand this imagery. So we can develop object detectors that can detect the dozens of objects that a child sees throughout their day as captured by a head-mounted camera. And so underneath the hood of these diverse applications are some technical themes, machine learning, especially deep learning these days, probabilistic graphical models, large-scale multimodal data, interesting interdisciplinary collaborations, and large-scale computation. And with that, I will say thank you.